Very good afternoon, students.
Good afternoon.
Without wasting any time, let us start with the discussion. If you remember, last class we have been discussing about the reactions of aldehydes and ketones with strong oxidizing agents, right? Oxidation of aldehyde with the strong oxidizing agent gives respective carboxylic acid. Similarly, if you try to do the oxidation of ketones also, you will be getting the respective carboxylic acid, and that is going to be following the Popoff's rule. And as I have told you, the aldehydes can be oxidized with the help of milder oxidizing agents also. But to oxidize ketones, always a stronger oxidizing agent is required. Why? Because in aldehydes, we have an oxidizable hydrogen, whereas in ketones, such oxidizable hydrogen is not present. That is the point. So the milder oxidizing agents are Tollens reagent, failing solution, and bending solution. So what is Tollens test? What is Tollens test? If you start with the Tollens test, Tollens reagent is a ammonical silver nitrate solution. The aldehydes, like this is also Tollens reagent, bending solution, failing solution, all these are again respective milder oxidizing agents. So what happened to the respective aldehyde? That aldehyde will be converting into respective carboxylate or carboxylic acid. You will be getting a carboxylate or carboxylic acid upon treating aldehyde with milder oxidizing agents also. So first starts with the Tollens reagent. Tollens reagent is a ammonical silver nitrate solution. Ammonical silver nitrate solution means you can write that as AgNO3 plus NH4OH, RCHO, AgNH3 taken twice OH. So we can have these type of reactions. I can give AgNO3 plus NH4OH. AgNO3 plus NH4OH will be giving Ag2O. Ag2O plus NH4NO3. This Ag2O can be reacting with Ag2O can also react with NH4OH to form AgNH3 taken twice OH. This is nothing but a Tollens reagent. I can mention Tollens reagent as mixture of AgNO3 and NH4OH. I can also mention this particular complex AgNH3 taken twice OH, or I can also mention Ag2O. Under all the three conditions, we have to form the respective carboxylate only. So RC double bond H, RCHO means RC double bond OH. The CH bond will be cleaved. You will be getting COH. Again, ammonical silver nitrate solution. We have NH4OH also. The base will pick up the proton, forming respective RC double bond O minus NH4 plus. This is going to be formed. Along with that, silver is going to be having a precipitate. That means silver mirror is obtained. So RC double bond O minus NH4 plus Ag silver mirror is going to be obtained. Tollens reagent means ammonical silver nitrate. They can mention AgNO3 plus NH4OH or AgNH3 taken twice OH or Ag2O. Under all these three conditions, you have to convert the respective aldehydes to respective carboxylates. And if they have mentioned the acidic condition also, like RC double bond OH Ag2O, this is the first reagent, and second reagent, let us say H plus. In that condition, first you will be getting what? RC double bond O minus, the carboxylate acidified, you will get RC double bond OH plus Ag, silver mirror is obtained. Is that clear, students?
Yes.
Okay. Tollens reagent, you have to understand few points. Tollens reagent will not affect the unsaturation present in the substrate. First point, Tollens reagent will not affect the unsaturation in the substrate. Second point, using Tollens reagent, I can distinguish between aldehydes and ketones, but a Tollens reagent will be shown. That means Tollens test will be shown by both aliphatic and aromatic aldehydes. Thus, you cannot distinguish between aliphatic and aromatic aldehydes. Second point, Tollens test is shown by both aliphatic and aromatic aldehydes. And not by ketones. Okay, tolerance reagent or tolerance test will be not affecting the unsaturation. Tolerance test will be shown by both aliphatic as well as aromatic aldehydes, and it will not be shown by ketones, right? Example, CH3, CH double bond, CH, CHO. The unsaturation, is it going to be disturbed? No. We have CHO, first a tolerance reagent and then acidic hydrolysis. You will get what? CH3, CH double bond, CH, C double bond OH. This is going to the major product. We should get the carboxylate, but again, second acidic hydrolysis they have mentioned. So clearly we have to find the respective carboxylic acid, not the carboxylate. C double bond O, Ag2O, and then H plus, H3O plus. You will be getting what? Respect to C double bond OH is going to be formed. Benzoic acid will be obtained from the respective benzaldehyde. Benzaldehyde upon treatment with milder oxidizing agent like tolerance reagents, you will get the benzoic acid and you have to do the acidic hydrolysis. Right? Conditions, tolerance test is given by aldehydes, aliphatic plus aromatic both, but not given by ketones. Hence, we can distinguish aldehydes, aliphatic and aromatic aldehydes from ketones. Using tolerance test, we cannot distinguish aliphatic and aromatic aldehydes because both are giving the positive test. And tolerance test is also given by few compounds like hemiacetal, formic acid, and alpha hydroxyketones. Right on that point. Tolerance test will be given by hemiacetal, formic acid, alpha hydroxyketones, and not given by hemiacetal will give positive, formic acid will give positive, alpha hydroxyketones will give positive. And I'll mention the condition with respect to alpha hydroxyketones. Not every alpha hydroxyketone, only few. We'll mention that. But acetal, if you go with acetal, in the hemiacetal we have what, students? R, CH, OH, OR dash. Formic acid, HC double bond O, OH. Formic acid, whenever you treat, you will be getting respect to carbon dioxide. Acetal, if you treat with Ag2O, negative. Acetal will have structure R, CH, OR dash, OR dash. Okay, acetal will give negative. Acetic acid, only formic acid will give positive. Acetic acid also negative. So now look at the alpha hydroxyketones. Alpha hydroxyketones which can convert to aldehydes will give positive result for tolerance test. Alpha hydroxyketones which can convert to alpha hydroxyketones which can convert to aldehydes will give positive results for tolerance test. That means let us take an alpha hydroxyketone. Generally, alpha hydroxyketones which should be having a positive tendency, like which has a tendency to convert to aldehydes, they will be giving positive test. How is that going to happen? Let us look at the scenario now. Let us take CH3, C double bond O, CH2H. Because C double bond is a functional group, with respect to C double bond O, on the alpha carbon we should have OH group. CH3, C double bond O, CH2OH. This is an alpha hydroxyketone or not? This is the alpha carbon. On the alpha carbon we have OH group. Now base, ammonical silver nitrate solution. So ammonia, whenever it is added to water, it forms NH4OH, which is acting as a base. So base can pick up this proton. Like with respect to C double bond O on the alpha carbon, whatever the CH bond is there, is that going to be a polar bond? Yes, it is. Why? Because we all know that C double bond O pi electron density is moving towards oxygen, developing partial negative on oxygen and partial positive on carbon. Because of partial positive on carbon, this carbon-carbon electron density is moving, developing delta plus plus on this particular carbon. Because of that, the CH electron density is moving where delta positive is developed on hydrogen. So base will try to pick up this proton. As soon as base picks up the proton, what happens? The CH electron density is given to carbon. So if you can just write down the product, you will be getting CH3, C double bond O, CH, OH, and a negative charge. Base picked up the proton. And if you try to draw the resonating structure, negative charge on carbon and C double bond of pi electron density, they were in resonance. So the negative charge on carbon comes into the C double bond of pi electron density moves away. So if you can try to write the respective resonating structure, you have CH3CO minus, C double bond C, CH as it is, and COH. This is nothing but the respective resonating structure. Yes or no? What is this called as? CH3 C double bond O minus C double bond CH OH. What is this called as? Enol. Is it similar to enol system or not? Is that similar to enol system? But what we have lost? If it is enol, we should have C double bond C OH. But here we have O minus. So that is why it is called as enolate. It is a salt. It is nothing but enolate. If you look at this CH3 C double bond C, COH and CO minus, this negatively charged oxygen, can it pick up this proton? Yes or no? That negatively charged oxygen that can pick up this proton. Why I am calling this as a proton? Because of again the polarity CO bond, like OH electron density moving towards oxygen. So O minus picks up this proton. If O minus picks up that proton, you will get what? CH3 COH C double bond C CO minus CH. CH3 COH C double bond C CO minus CH. And now this can pick up a proton from the water. Like O minus, we have water in the reaction mixture, we have water. O minus can pick up the proton. So loss of OH minus, generating CH3 COH double bond COH CH. And can you write the respective tautomer of this? C double bond COH. If you can try to write the respective tautomer, you will get CH3 COH. You get CH here. Yes or no? CH double bond O. CH3 CHOH, like this is enol. This is a respective keto. You can look at this particular structure, students. Initially we started with the compound CH3 C double bond O CH2OH. It is an alpha hydroxy ketone. Alpha hydroxy ketone. This alpha hydroxy ketone, upon treatment with the base, it undergo inlet formation, which can be trying to picking up the proton, which can be forming the enol structure. The enol can be converted to respective ketone. It is a keto form. But what it is an aldehyde or not? Yes or no?
Sir.
The alpha hydroxy ketone has been converted to respective aldehyde. So this aldehyde can show tolerance test or not? So alpha hydroxy ketones which can convert to aldehydes will give positive result for tolerance test. Will give positive result for tolerance test. This is a point you need to understand. I'll be giving one more compound known as benzoin. Benzoin is this particular compound. Will it give positive result for tolerance test? C double bond O, CHOH. This is nothing but your benzoin. Will it give positive? It is alpha hydroxy ketone or not? Benzoin C6H5 C double bond O CHOH C6H5. It is an alpha hydroxy ketone because with respect to this C double bond O, this is alpha carbon and the alpha carbon OH is there. What actually happens is wherever we have alpha carbon, there you have to keep the C double bond O, students, and you have to remove the CO bond is there, right? That is converted into C double bond O. C double bond O is converting into COH. Even though you on the alpha carbon you get a double bond O, is that a aldehyde? Even though on the alpha carbon we get a C double bond O, is that an aldehyde? No. So alpha hydroxy ketone benzoin is an alpha hydroxy ketone which is not going to give positive result. Okay. Even though benzoin is alpha hydroxy ketone, it will give negative tolerance reagent, negative tolerance test. Why? Reason is simple, because benzoin, even though you try to write the respective tautomerase structure, you are not getting aldehyde. Okay, it will give negative tolerance test as it will not give aldehydes. Right. So this is the tolerance test. AgNO3 have taken. To that AgNO3 you are adding dilute NaOH. And dilute ammonia. And the unknown solution we have added. And if you try to heat it, and that will indicate the unknown solution to be an aldehyde. It can be an aliphatic aldehyde or an aromatic aldehyde because it leads to the formation of silver mirror. Right. Next type of milder oxidizing agents are Fehling's and Bendix test. Fehling's solution, Bendix solution. So Fehling's A, Fehling's B, Bendix A, Bendix B. Fehling's A is CuSO4.5H2O. Bendix A is CuSO4.5H2O, which are deep blue in color. Fehling's A, Fehling's B, and Bendix A, Bendix B have seen. Fehling's B is sodium potassium tartarate, Rochelle salt. Bendix B is sodium citrate. So only aliphatic aldehydes will give or will react with the Fehling's and Bendix agent and convert the blue color complex to red color, and red color is due to the formation of Cu2O. So why this Fehling's A and Fehling's B, whenever you add, they will form a complex. Like what type of complex is going to form? CuSO4.5H2O is already deep blue in color, but CuSO4.5H2O will be reacting with the respective sodium potassium tartarate. And if it reacts with sodium potassium tartarate, it will form a complex in this manner. CuO, like CuOH taken twice, CuOH taken twice plus C double bond ONA, C double bond OK, C double bond O minus Na plus is connected to C, connected to CHOH. It is also connected to CHOH, connected to C double bond O minus K plus. This is nothing but your sodium potassium tartarate. They too will react with each other to form a complex in this manner. CuO, CuO, CH, CH, C double bond O minus Na plus, C double bond O minus Na plus, which is also a blue colored complex. Blue colored complex. This blue colored complex will be reacting with the respective R C double bond OH aliphatic aldehydes, react with the complex to form Cu2O, which is a red PPT. Okay. What is going to happen to the respective RC double bond OH? Since this is complex is also going to be oxidizing agent, it will convert the respective aldehydes to respective carboxylates. So RC double bond OH will be converted into RC double bond O minus, and Cu2O is going to be released out. Cu2O is going to be released out. So these are the reactions. I have written the complex for the respective Fehling solution. Similarly, a different type of complex is going to be blue colored complex is going to be formed with Bendix. So Bendix also, like deep blue color complex, it will also react with aliphatic aldehydes to convert to respective carboxylates, and Cu2O is going to be released out, which is a reddish brown colored PPT, reddish brown colored precipitate. Yeah, aliphatic aldehydes, Fehling solution deep blue. It will form milder oxidizing agent. So it will convert the respective RC double bond H to RC double bond O minus Na plus and Cu2 is released out. Same Bendix solution, deep blue color, RC double bond H aliphatic aldehydes will convert to respective carboxylate RC double bond O minus Na plus and Cu2O reddish brown PPT. You can write down here only aliphatic aldehydes will give positive test. That means aromatic aldehydes like benzaldehyde and different other aldehydes, substitute benzaldehyde, do not react to Fehling's or Bendix test due to more alkalic nature of these reagents. Aliphatic aldehydes do not react with Fehling's or Bendix reagents due to more alkaline nature of these reagents. Since these reagents are more alkaline, they can only be reacting with the respective aliphatic aldehydes, not with the aromatic aldehydes. And that is what you can obtain. The Cu2O is going to be obtained as a reddish brown PPT, which will indicate the presence of aliphatic aldehydes. Tollens reagent, Fehling's, Bendix, they won't react with ketones. First point. Tollens can react with both aliphatic as well as aromatic. Bendix and Fehling's will react only with aliphatic aldehydes. And in the Fehling's or Bendix, the deep blue colored complex are going to be converted to reddish brown PPTs. In the tollens, you will get a silver mirror and same RC double bond OH convert to RC double bond O minus. Is that clear, students? The milder oxidizing agents, how they are going to convert the respective aldehydes to carboxylates?
Yes.
Yes, sir.
Yes, right. Very good. Same, you can look at the animation and you will have the same scenario. Next, if you go with the Skiff's test, aqueous solution of para-rosazilyl hydrochloride, that is known as Skiff's dye, which is actually pink colored. This Skiff's reagent is Skiff's dye plus SO2. Understand this point carefully. Skiff's dye plus SO2, para-rosanilin hydrochloride, that is nothing but your Skiff's dye, and mechanism is not required here. Skiff's reagent is Skiff's dye plus SO2. Whenever SO2 is actually passed through Skiff's dye, aqueous solution of para-rosanilin hydrochloride, this which is actually pink color in nature, whenever that is passed through SO2, that will form a different type of complex which is going to be colorless. So Skiff's reagent is Skiff's dye plus SO2. This will be colorless in nature. Skiff's dye will have a pink color, but the Skiff's reagent is colorless because with the passage of SO2, the color is going to be lost. This Skiff's reagent is colorless, right? This colorless Skiff's reagent, whenever is treated with an aldehyde, you will generate the pink color. That means pink color is going to be restored. In that condition, you can say, so this is also going to be used to detect the respective aldehydes and ketones. Skiff's reagent, which is colorless, that upon treatment with aldehydes, it will form again. That means it will restore the pink color. If a particular unknown compound restores the pink color of Skiff's reagent, because in the Skiff's reagent we have Skiff's dye plus SO2, right? That means if you are indirectly removing the SO2, only Skiff's dye is going to be obtained. That means SO2 is reacting with RC double bond H. That means whenever Skiff's reagent, a colorless Skiff's reagent, upon treatment with RC double bond H, if a pink color is restored, then we can say that particular unknown compound is an aldehyde. So this is also used to distinguish between aldehydes and ketones, and this was your respective Skiff's test. Right. Next reaction, oxidation of methyl ketone or haloform reaction. Haloform or iodoform reaction, very famous reaction. Aldehydes and ketones having one aldehyde and ketone having at least one methyl group linked to carbonyl carbon atom or methyl ketones are oxidized by sodium hypohalite, that means NaOX, to sodium salts of corresponding carboxylic acid having one carbon atom less than the carbonyl compound. How is this happening? That we want to understand. CHCl3 chloroform, CHBr3 is bromoform, CHI3 is iodoform. Let us look at the reaction first. RC double bond of CH3, RC double bond of CH3, CH3 I can write as 3 CH bonds treated with 3 mole of X2 and 4 moles of NaOH. What is going to happen, students? The OH minus, like whatever the OH minus we have in the reaction mixture, that will try to pick up this proton. It is the RDS. That means it is a slowest step RDS. The rate determining step is OH minus picking up the proton. As soon as OH minus picks up the proton, the CH electron density is given to carbon, leading to the formation of RC double bond O CH2 minus. OH minus picked up the proton and it will lead to the loss of H2O. H2O plus. Yes or no? That means H2O is lost. OH minus will pick up this proton. Why OH minus can pick up this proton? The same reason what I have told you earlier in the alpha hydroxyketone. Because the C double bond is polar in nature, this carbon-carbon bond becomes polar. Ultimately, the CH bond becomes polar. So OH minus picks up the proton. So CH electron density is given to carbon. Now what is going to happen is we have halogen, right? X2. Let us take I2. The negatively charged carbon can now be reacting with one of the iodine atoms to convert the CH bond to respect to Ci bond, and iodide is lost. Loss of I minus occurs. That means I2 is actually a non-polar species, but upon reacting with respect to enolate, this is an enolate. RC double bond of CH2 minus is an enolate. Why? Because we have this particular resonance. RC O minus C double bond CH2. This is nothing but enolate. Yes or no? So the negatively charged carbon that can be attacking the iodine, loss of iodide will occur. You will have R C double bond O CH2 Ci. Now can I say with 1 mole of OH minus and 1 mole of I2, can I say ultimately the CH bond on the alpha carbon that has been converted to Ci bond? Yes or no? The CH bond has been ultimately converted to Ci bond with how many moles? 1 mole of base and 1 mole of halogen. If I react with 2 more moles of base and 2 more mole of halogen, can I say the remaining 2 CH bonds can also be replaced by 2 Ci bonds? Can I say like this? 2 more moles of base and 2 more moles of halogen will form R C double bond O C I C I C I, because these 2 other CH bonds, whatever they are present, they are also going to be replaced. Now what is going to happen is, now we still have up to now how many moles of NaOH we have used? 3 moles. How many moles of halogen? 3 moles. Now the 4th mole of NaOH or 4th mole of base, that OH minus, is now going to act as a nucleophile. This OH minus will try to attack this electrophilic carbon. C double bond electron density moves away. We generate RCO minus COH Ci3. Ultimately, the negative charge on oxygen comes into Ci3 is a good leaving group. So negative charge on oxygen comes into this carbon-carbon single bond that is going to be given to carbon. So we generate RC double bond OH plus Ci3. Do we have any charge on the carbon of Ci3? Do we have any charge on the carbon of Ci3? Negative charge should be present or not?
Negative.
Because the carbon-carbon electron density is taken. So this negatively charged Ci3 minus, that will try to pick up this proton, leading to the formation of what? R C double bond O minus plus CHI3. That means with the 4 moles of NaOH and 3 moles of X2, you are getting the conversion of respect to RC double bond of CH3 to RC double bond O minus Na plus. That means you are getting a carboxylate, and along with that CHX3 is released, haloform is released. Here I have taken iodine, so iodoform is released. Iodoform is a yellow solid. If I take bromine, bromoform is a liquid, and if I take chlorine, you will get a chloroform. It is also a sweet smelling liquid. And this was a mechanistic approach. What is the condition? We should have C double bond O CH3 group for the respective aldehydes or ketones to show aldehydes or ketones, to show positive haloform test, they should have CH3 C double bond O group. Mechanism, the same mechanism, whatever you're going to explain. R C double bond O CH2, OH minus picks up this proton, CH electron density will be given to carbon, developing negative charge on the carbon. That will be treated with X2. You will generate loss of halide will occur. You generate R C double bond O CH2X. Actually, this is resonance stabilized. RCO minus C double bond CH2, which is nothing but inhalate. Again, one more mole of OH minus, one more CH bond is going to be picked up. You get CH minus. Again, one more mole of X2 forming RC double bond of CHX2. Again, the third mole of OH minus forming RCH. That CH bond again lost. CX2 minus. That will be reacting with X2 to form RC double bond of CX3. Now the fourth OH minus is now going to act as a nucleophile. It will attack the electrophilic carbon. Pi electron density moves away. RCO minus COH CX3, negative charge comes into CX3 minus lost. You will generate RC double bond OH plus CX3 minus. That will ultimately lead to the formation of RC double bond O minus and CHX3. Got this or not? Mechanism, same mechanism, whatever we have discussed.
Yes, sir.
Yes, right. So this was the mechanistic approach for the respective conversion of C double bond O CH3 to aldehydes or ketones which have CH3 C double bond O group will give positive iodoform test. Iodoform or haloform, you can write positive iodoform test. And there are some alcohols which are going to give this positive test. Which alcohol can give positive test?
Ethanol.
Ethanol. Why? Like those alcohols which can be, like I can give this total reagent as NaOH plus X2, you can write, right? This NaOH plus X2 you can write as NaOX. This NaOX is a milder oxidizing agent. Milder oxidizing agent. If I take NaOX, which is acting as a milder oxidizing agent, that can be converting the alcohols to respective carbonyls or not. Like if I take CH3 CHOH group alcohol, that can be converted to CH3 CHOH group can be converted to CH3 C double bond O group in the presence of NaOX. That means if I take alcohols which contain CH3 CHOH group, since NaOX is a milder oxidizing agent, that will convert the CH3 CHOH group to CH3 C double bond O. Whenever we have CH3 C double bond O, that will give positive iodoform test or positive haloform test. Now you can answer the question like CH3 CH2OH, it will give positive or negative haloform test. I can write this ethanol as CH3 CHOH and the other connection is hydrogen. So it has this group. So it should be giving positive iodoform test. Okay, the alcohols which are going to have CH3 CHOH group, they can be converted to CH3 C double bond O. Why? Because NaOX, whatever you are saying, that is a milder oxidizing agent. I'm saying it is a milder oxidizing agent, so it will convert the alcohols to respective carbonyls only, not the acids. So the alcohols which can be converted to respective carbonyls which contain CH3 C double bond O group, they can also give the positive iodoform test. And ketones, methyl ketones will give positive haloform. Aldehyde means only acetaldehyde will give, because in acetaldehyde only we have CH3 C double bond O, no other aldehyde will have that group. And alcohol which contains CH3 CHOH, right? So when methyl ketones react with halogen in the presence of excess base, multiple halogenation always occurs at the carbon of methyl group. Note the CX3 minus is a good leaving group. That is why negative charge on oxygen comes into CX3 minus lost. When the halogen used is iodine, the haloform product iodoform is a solid that separates out as a yellow precipitate. Hence, this reaction is also used as a test for methyl ketones, not only for methyl ketones, but also for all those groups which contain CH3 C double bond O. And how we can, like what type of reagents you can take? You can take Cl2 plus NaOH, Br2 plus KOH, I2 plus NaOH, Cl2 plus COH taken twice. like NaOCl, NaOBr, NaOI, CaOCl2, all these can be mentioned. These are all the reagents which are useful for the respective iodoform test. I can give X2 plus NaOH, or I can mention the same X2 plus NaOH as NaOX, because NaOH reacts with X2 to form NaOX and NaX and H2O. NaOX and NaX and H2O. Right, students? Ketones, methyl ketones undergo haloform reaction because they possess CH3 C double bond group. Aldehydes, only acetaldehyde will give, because only acetaldehyde only we have CH3 C double bond. Is there any aldehyde which have CH3 C double bond group? Is there any aldehyde which have CH3 C double bond group? No other aldehyde, right? So that is why only acetaldehyde will give. Alcohols which contain CH3 CHOH group, they will also give. Why? Why alcohols containing CH3 CHOH will give?
NaOX is a mild oxidizing agent.
Yeah, because NaOX is a milder oxidizing agent. Very good. That's what NaOH plus X2 is a milder oxidizing agent. NaOH plus X2 can also be written as NaOX. NaOX is a milder oxidizing agent. So ultimately we have CH3 CHOH CH3 NaOX converts to CH3 C double bond to CH3 CH3 CH2OH, because here also in the alcohol we have CH3 CHOH group. Here also we have CH3 CHOH, but the carbon is again connected with hydrogen. So that will also give positive iodoform test. They will all give the positive iodoform test. Right? Let us look at some examples also. CH3 CH double bond C CH3 C double bond to CH3 NaOCl. What will happen? NaOCl means you can understand this as NaOH plus Cl2. That means they are talking about a haloform reaction. C double bond to CH3 group is present. So the C double bond to CH3 group will be converted to respective. NaOX is a milder oxidizing agent. Milder oxidizing agent treated with a methyl ketones will form respective carboxylates. You get C double bond O minus, carboxylate is obtained. C double bond O minus, that will develop electrostatic force of attraction with Na plus. Yes or no? Which of the following compounds will give positive iodoform test? Look at these compounds. Which of the following compounds will give positive iodoform? Compound A will give or not?
Yes, sir.
CH3 C double bond group, it will give. Compound B,
Yes.
CH3 C double bond group is there, so it will also give. Compound C, pH C double bond pH,
No, sir.
no, it will not give. Compound D, CH3 C double bond group, it will give.
Yes.
Compound D,
No.
it will not give because it's already carboxylic acid, so you will get A, B, D as the right options. A, B, D. Which of the following compounds will give positive iodoform test?
E will give.
E will give, and any other compounds?
Yep.
Compound B, look at compound B, CH2 I C double bond H. Compound A will not give, obviously. Can I eliminate this? CH3 CH2 C double bond H, because CH3 only acetaldehyde will give, it will not give. Compound B, look at CH2 I C double bond H, it will give or it will not give. You should not get confused like, sir, CH3 C double bond H is not there. No, so then why you can say B will give? B will give because already one of the CH bond is replaced by iodine. Remaining two CH bonds can also be replaced by iodines. Yes or no? This is one of the intermediate in the reaction mechanism. Like if this is obtained from CH3 C double bond H only, CH3 C double bond H, whenever it is react with one OH minus and one X2 or one I2, it will form respective CH2I C double bond H. So remaining two CH bonds can also be replaced with the two more moles. 2OH minus 2I2 will form CI3 C double bond H. So compound B, it is similar to CH3 C double bond H only, but one of the intermediate is given. So compound B will give. You should not think like CH3 C double bond H is not there. No, it is actually the CH3 C double bond H where converted one mole is already reacted. So this will also give the positive iodoform test. Compound C, PHCH2OH, will it give?
No.
Why it will not give? Because we don't have CH3 CHOH group. CH3 so CHOH not present, so it will not give. Compound E, lone pair of electron present on nitrogen. Although you think like CH3 C double bond is present, but lone pair of electron present on nitrogen, they were in resonance or not? So if you try to draw the respective resonating structure, you get CH3 CO minus C double bond NH2 with a positive charge on nitrogen. So the amide systems, they will not give. Why? Because that is due to the resonance. This carbon is going to be less electrophilic, and that is why it will not give. Look at this CH3 CHOH group is there, so that will give CH3 CHOH. Compound F CH3 CHOH group is there, so that will also give. So compound B, compound E, compound F will give the positive iodoform test, whereas compound D, A, and C will not give. Is that clear, students?
Yes, sir.
Look at this scenario. So there are the total types of reactions. So starting with acetophenone treated with NaOI H plus gives A plus B. B is yellow PPT. B treated with Ag upon heating form C. C dilute H2S4 form D. D NH2OH form in the presence of H plus form C. What are A, B, C, D, E? What is A first of all? Like CH3 C double bond group we converted to NaOH. That is NaOI means NaOH plus I2. NaOH plus I2. That means they are doing iodoform reaction. Iodoform means you'll get what? First you should be getting C double bond O minus Na plus, and again acidification is there. If you do the acidification, you get C double bond OH. Along with that, you are getting LOPPT. What is that LOPPT, students?
CHI.
CHI3. So what is A? A is nothing but your benzoic acid. What is B? B is nothing but your CHI3. So A is benzoic acid, B is CHI3. So that compound B LOPPT treated with silver upon heating, CHI3 plus Ag plus CHI3. It will form what?
Time.
HC triple bond CH. Yes or no? All the AGI is going to be released out. This ethine, this is your compound C. Compound C treated with dilute H2S4. Whenever they have mentioned H2SO4 compound C, they should also mention Hg2. Okay, then only the question is going to be right. Directly water is not going to be added to alkynes. In the acidic medium, we should add some catalyst like mercuric 2 salts. So you will be getting what? HCOH double bond CH. That means water is added. So now if you try to write the respective enol and keto tautomerism, you will be generating HC double bond CH3. CH3 C double bond H, this is nothing but your compound E. CH3 C double bond H, compound E. CH3 C double bond H treated with NH2OH. NH2OH, ammonia derivative. Ammonia derivative means you have to maintain weakly acidic medium or strongly acidic medium.
Weakly acidic.
Weakly acidic medium we have to maintain. The oxygen and the two hydrogens from nitrogen, they are going to be lost. You will generate CH3 CH double bond N OH, which is nothing but your compound E. So these are your respective A, B, C, D, E. Okay. And A should be C double bond OH, not ONA. Why? Because you are doing the acidification also. And next type of chemical reactions are chemical reaction due to the presence of alpha hydrogens. So different types of reactions we have seen, students. After the oxidation reactions are very important. After that, we have the chemical reactions of aldehydes due to the presence of alpha hydrogen. Under this category, what type of reactions you are going to expect?
Aldol condensation, Cannizzaro reaction.
Very good. Aldol condensation, Cannizzaro reaction you will be having. So acidity of alpha hydrogen of carbonyl is due to strong electron withdrawing effect of carbonyl group. Simple thing, if you take carbonyl group or C double bond of CH3 I have taken, the C double bond of pi electron density is moving towards oxygen greatly. Because of that, you get a partial positive charge on the carbon. Because of partial positive charge on the carbon, the Cc electron density, the carbon electron density is moving toward this carbon. Because of that, this carbon gets delta plus plus. Because of the delta plus plus, the CH electron density is moving, developing partial positive charge on the hydrogen. Because of the partial positive charge developed greatly on the hydrogen, whenever you treat this with the base OH minus picks up the weight, CH electron density is given to carbon. You generate R C double bond O CH2 minus. This negative charge on the carbon will be in resonance with the C double bond of pi electron density, forming RCO minus C double bond CH2. Right? This is nothing but your respective inlet. R C double bond of CH3 treated with OH minus forms R C double bond of CH2 minus. That will have the respective inlet ion. And here OH minus picked up the proton means water is lost. This negative charge on the carbon that can be attacked, that can be acting as a nucleophile, and it can attack any other species. Is that point clear or not? Is that point clear? Right. So first question, in the aldol condensation, what is going to happen is aldol and aldol condensation reaction, aldehyde and ketone having at least one alpha hydrogen undergoes a reaction in the presence of dilute base to form beta hydroxyaldehyde or ketone respectively. This is nothing but aldol. If it is a aldehyde, we call aldol. If it is a ketone, you form ketol. Beta hydroxyaldehyde is aldol. You can write down here. Beta hydroxyaldehyde is aldol. Beta hydroxy ketone is ketol. Understand this point carefully. Aldehydes and ketones having at least one alpha hydrogen undergoes a reaction in the presence of a dilute base to form beta hydroxyaldehyde or ketone. Beta hydroxyaldehyde is said to be aldol. Beta hydroxyketone is said to be ketol. First step is same. Base will try to pick up the proton to form a respective inlet. The inlet which is formed, that will be acting as a nucleophile, and it will attack the next molecule of the aldehyde or ketone to form the beta hydroxyaldehyde or beta hydroxyketone. Whenever you mention the heating condition, it will undergo dehydration to form a carbon-carbon double bond. And how we should form the carbon-carbon double bond? How we should do the elimination? The elimination you have to do in such a way such that the carbon-carbon double bond, whatever you are forming, that should be in resonance with the C double bond O. That should be in conjugation with the C double bond O. You don't go with the sets of rule and all. The carbon-carbon double bond, whatever you are following, that has to be in conjugation with C double bond O. And what type of base you have to choose? NaOH, KOH, CaOH taken twice, BaOH taken twice, aqueous Na2CO3, aqueous K2CO3, C2H5ONa. These are the respective bases which you can choose. And if you look at the reaction carefully, aldehydes and ketones having at least one alpha hydrogen undergo reaction in the presence of a dilute base. Why can't a strong base? Can we take a strong base? Can I take a strong base? Instead of dilute NaOH, can I take concentrated NaOH? Because concentrated NaOH will pick up the proton more fastly, right? Can I do it? So let us start with the reaction. You'll get an idea. Let us take first acetaldehyde, CH3, C double bond OH. I have added base, OH minus dilute. It forms what? CH2 minus C double bond OH. The CH2 minus C double bond OH will react with one more molecule. H C double bond O CH2 minus will be acting as a nucleophile. It will attack the next molecule of CH3 C double bond OH. As soon as it attacks, the C double bond of pi electron density moves away. You will generate H C double bond of CH2 is connected to carbon. Carbon is connected to O minus, also connected to CH3CH. It picks up the proton from the solvent, forming HC double bond O CH2 COH CH3. This is C double bond group. This is alpha. This is beta. On the beta position, you have OH group. So what is this called as? Beta hydroxy aldehyde, which is nothing but aldol. Yes or no? Everyone got the mechanistic approach. Base picks up the proton, forming the respective inhalate. The CH2 minus is now going to attack the carbon. Nucleophilic attack, nucleophilic addition is going to happen to form the respective aldol. Is that clear or not, students? Try to respond.
Yes, sir.
Yes, sir.
Yes.
Question is simple. Instead of dilute base, can I take a strong base? Because strong base can pick up the proton even greatly. What, Varshita? Can I take a strong base? See, understand this point carefully. If I take a strong base, what is going to happen is, you understand the scenario carefully. The OH minus, whatever it is going and picking up the proton, that will form the respective inhalate. If I take a strong base, the strong base will react with all the aldehydes and form the respective inhalates only. Understand this. The inhalate is formed, right? That inhalate is also basic in nature. The inhalate is a stronger base and a stronger nucleophile when compared to OH minus. Whatever the base you are considering, if that base is a stronger base, it will convert all the aldehyde molecule to respective inhalates. But if that base is a weaker base when compared to the inhalate, what happens? First, let us say 100 molecules are there. Out of 100, let us say one molecule has been converted to inhalate. And in the solution, we have OH minus inhalate. If this OH minus, whatever the base you are taking, if that is a stronger base, that will try to convert all the 100 molecules to 100 inhalates. But the inhalate, the base, whatever you are considering, that should be a weaker base when compared to inhalate. Then only the inhalate can react with the next molecule. The base will initiate the formation of inhalate, but inhalate, once it is formed, that will have to react, not the base reaction has to be happening. Understood this point or not, all of you?
Yes, sir.
Okay, the base, whatever you are taking, if it is a strong base, it will convert all the aldehyde to respective inlets. Sorry. If the base is a strong base, it will convert all the aldehydes to respective inlets. No question of condensation, aldol condensation. If the base is a dilute base, it has to be dilute enough so that the inhalate is more basic when compared to respect to OH minus. So inhalate can act as a nucleophile and attract the electrophilic carbon, not the base picking up the proton. Right? Next aldol, CH3 C double bond OH, acetaldehyde, I have treated with dilute NaOH. It forms CH3 CHOH CH2 C double bond OH. Beta hydroxyaldehyde or aldol is obtained. Same if I take with acetone, you will get this reaction. Acetone CH3 C double bond O CH3 treated with OH minus. It forms what? CH3 C double bond O CH2 minus. This CH3 C double bond O CH3 reacting with CH3 CH2 minus C double bond O CH3. The CH2 minus attacks the electrophilic carbon C double bond O pi electron density, moves away, generate CH3 CO minus CH3 CH2 C double bond O CH3. It picks up proton from the water, forming CH3 COH CCH3 CH2 C double bond O CH3, which is nothing but alpha beta On the beta position, beta hydroxy ketone. Beta hydroxy ketone is nothing but a ketone. Acetone upon treatment with dilute NaOH, it forms beta hydroxy ketone, which is nothing but your respective ketone. Understood this point or not, all of you?
Yes.
Yes, right. Mechanism is simple. Whatever the mechanism I'm explaining, the inlet is going to be formed. The CH3 HC double bond of CH2 minus is resonance stabilized. The inlet anion HC double bond of CH2 minus is attacking the respective carbon, leading to the formation of respective aldol or acetaldol. If you heat it, if you heat the aldol, like if you heat it in the acidic medium or in the basic medium, what is going to happen is the OH will be removed and the hydrogen is removed, such that you form a double bond. The double bond, whichever it is going to be formed, that should be in conjugation with C double bond O. So in the acidic or basic medium, you can heat it like CH3, CHOH, CH2, C double bond OH, beta hydroxyaldehyde. Whenever it is heated in the acidic medium or basic medium, it will form respective alpha beta unsaturated aldehyde, also called as crotonaldehyde. CH3, CH double bond CH, C double bond H. Like just a dilute NaOH means you should stop under alpha hydroxyaldehyde, beta hydroxyaldehyde, or beta hydroxy ketone. But heating mentioned means you have to do the elimination and form a double bond, and that double bond has to be in conjugation with the C double bond O. That double bond, whatever you are placing, that should be in conjugation with the C double bond O group. Right? And the shortcut you can mention beta hydroxy carbonyl compounds dehydrates readily under acidic as well as basic conditions. Dehydration will be ready because the C double bond C is in conjugation with C double bond O. And the shortcut what you can think of is, because the mechanism you can write if it is one type of aldol, but if I give a mixed aldol or crossed aldol reaction, in that case you will be having 4 types of products formed. So there you should know the shortcut. Like we have CH3 CH3 C double bond O CH3, CH3 C double bond O CH3, right? With respect to the C double bond O, on the alpha position, whatever the carbon is there, from that carbon you remove 2 hydrogens, and from the other carbon you remove the double bond O, that is oxygen of C double bond O, and connect these 2 carbons to double bond. So you get what? CH3 CH3 C double bond CH, C double bond O CH3, CH3 C double bond CH, CH3 C double bond O CH3 plus H2O. This is nothing but a product. Okay, you don't need to write the product like this whenever they have given single aldol, but a crossed aldol whenever given, you can't write the aldol mechanism for all the 4 types of reactions, right? So then you can use this shortcut and write the major product. Look at this reaction. CH3 C double bond OH, OH minus upon heating, what it will form? CH3 C double bond OH. According to trick, if you go CH3 CH C double bond O plus C double bond O CH CH CH3. Like with respect to one molecule, the oxygen should be lost. With respect to other molecule, 2 hydrogens from the alpha carbon, they should be lost. You will get CH3 CH double bond CH C double bond H, which is nothing but your crotonaldehyde. Crotonaldehyde. CH3 CH double bond CH C double bond O. CH should be there. Okay. Like 1, 2 carbons are there. 1, 2, 1, 2. Total 4 carbons should be there in the product. But here you are having 5. CH3 CH double bond CH C double bond O CH. That should be the respective major product. Okay, CH3 CH double bond CH C double bond H. That should be the respective major product. Is that clear, students? Is everything clear?
Yes, sir.
Yes, sir.
Try to solve this example. CH3, CH2, C double bond OH, dilute NaOH gives A, and upon heating gives B. Nothing but C2H5. You can write CH3, CH minus C double bond H is obtained whenever you treat this with base. This upon treating with next molecule, C2H5, C double bond H. Negatively charged carbon attacks this particular carbon, leading to the formation of C2H5, CO minus CH, CH, CH3, C double bond OH. It will pick up proton from the water, forming CH3, CH2, CHOH, CH, CH3, C double bond OH. This upon heating will form the respective alkene CH3, CH2, CH double bond, C, CH3, C double bond H. Always keep the double bond in conjugation with the C double bond O. So this is nothing but your compound A. This is nothing but your compound B. Compound A is CH3, CH2, CHOH, CH, CH3, C double bond OH. Compound B is CH3, CH2, CH double bond, C, CH3, C double bond OH. Got it? CH3, C double bond, CH3, dilute NaOH gives A. A upon heating gives B. So you can write the product. Shortcut with respect to shortcut, how you can write CH3, C double bond, CH3 plus CH3, C double bond, CH3. If I try to remove water, ultimately I can write CH3, CH3, C double bond, CH, C double bond, CH3. Yes or no? So this is nothing but a compound B, but they are asking A. A, how to find out? Before this, you should have COH and CH. What means a double bond formed here means on this carbon you should have OH, on this carbon you should have hydrogen, and A should be CH3, COH, CH3, single bond, CH2, C double bond, CH3. This should be respectively CH3, COH, CH3, CH2, CH2, C double bond, CH3, and B is CH3, CH3, double bond, CH, C double bond, CH3. Got it or not, A and B?
Yes, sir.
Yes, sir.
That's right. Dilute NaOH upon heating. So directly you can write what? One compound I can write C double bond O. Other compound what I can write? With respect to C double bond O, on the alpha position, whatever two hydrogens are there, those two hydrogens, this oxygen and two hydrogens, they are going to be lost. Loss of water occurs. You generate the 6-member ring, double bonded with the other carbon. You get C double bond O. This is nothing but a major product. Okay. This is nothing but your respect to major product. So like that, you can do the aldol condensation reaction. But I'll ask a question in the aldol condensation. What is the rate determining step? RDS.
Carbanion.
RDS is a carbanion or any other step.
Abstraction of alpha hydrogen by base.
Okay. That abstraction of alpha hydrogen by base will lead to the formation of respective carbanion or inlet intermediate. But the rate determining step is not that step. Rate determining step is nucleophilic addition. Because whatever the inlet is there, right? That inlet is going to be attacking the next molecule. The nucleophile, it is acting as a nucleophile. Nucleophile is attacking the electrophilic carbon. Understand this point carefully. RDS in the aldol condensation is the nucleophilic addition. RDS in the aldol condensation is the nucleophilic addition. But the inlet just supports that particular reaction. But inlet supports the reaction. That means why this is important. Whenever there are two possibilities, like we have two alpha hydrogens, I have to pick up one. Then in that case, you have to pick up that particular alpha hydrogen and you have to do the electrophilic nucleophilic attack, right? Based on the nucleophilic attack, like which particular C double bond is more reactive towards the nucleophilic addition reactions, with respect to that only the addition has to be done. We all know aliphatic aldehydes are more reactive. then aromatic aldehydes, then aliphatic ketones, then aromatic ketones. So you have to make the C double bond of aliphatic aldehyde as it is, and you have to generate the inlet in such a way that inlet will act as a nucleophile. It will attack the more reactive C double bond O, because rate determining step is the nucleophilic addition reaction. Cross or mixed aldol condensation. That means an aldol reaction that starts with two different carbonyl compounds. An aldol reaction that starts with the two different carbonyl compounds is called as a crossed aldol or mixed aldol. Unless specific conditions are involved, like if only one aldehyde have alpha hydrogen, other do not possess. If some specific conditions are there, then we can lead to the formation of only one type of product. If conditions are not mentioned, then we can say a crossed aldol can always lead to the mixture of products from pairing of carbonyl reactants, as the following example will be illustrating. In this example, what type of compounds you can get? CH3CHO plus CH3CH2CHO dilute NaOH upon heating. Like I can say, the inlet is formed from CH3CHO, and the CH3CHO itself acts as a nucleophile, itself acts as a carbonyl compound which is undergoing nucleophilic addition. So with respect to CH3CHO only we can get one product. With respect to CH3CH2CHO only we can get one product. And inhalate from CH3CHO attacking CH3CH2CHO. Inhalate from CH3CH2CHO attacking CH3CHO. How many products you can get?
4 products.
Four products are going to be obtained. Yes or no? And those products will be looking like this. Like CH3 C double bond OH and CH3 C double bond OH. Like self condensation. CH3 CH double bond CH C double bond OH. It is self aldol because same molecules forming inlet and undergoing the nucleophilic attack. Same CH3 CH2 C double bond OH. C double bond OH CH2 CH3. It is also again self condensation. Simple or self aldol. If one is forming the inlet, like which is forming the inlet, CH3 CH2 C double bond OH. Here the alpha hydrogen is picked up, right? So it is forming the inlet, and the acetaldehyde is acting as is undergoing the nucleophilic attack. There you will get the crossed products. This is a crossed aldol. It's not a self aldol. And same, acetaldehyde can produce inlet. Acetaldehyde can form the inlet and attack the respective propanaldehyde, generating again a crossed aldol. So four types of products are going to be obtained. Four types of products are going to be obtained whenever you try to do the like two different types of aldehydes which possess both alpha hydrogens are taken, you will get four types of products. Everyone got this or not, students?
So,
Yes, please.
sir, you mentioned that when the inert ion is formed and acts like a nucleophile, it attacks the more reactive carbonyl center, right? Why is that the most important step? Because if inhalate is formed, it has to attack anyway, no?
Yeah, that's what. No. So everything depends upon what? Whatever the steps we are writing here, lot of steps we are writing it. Everything depends upon what? Ultimately, if you go into the root scale, everything depends upon rates. Rate of the reaction matters. Rate of the reaction matters means which step of the reaction is actually happening the slowly. That will be the rate determining step. So that has to be observed experimentally. Which step is the rate determining step? Which is the slowest step? If that particular step is the slowest step, in that particular step, whatever the nucleophile or whatever the C double bond group is there, which is more towards nucleophilic attack, that will be present, or that will be the major attack. Are you getting this or not?
Yes,
so we have
sir.
to know the rate determining step first. Rate determining step, lot of rate determining step we have seen in different types of reactions. You may ask a simple question, like whenever I said the free radical substitution also. So you are saying that hydrogen has been picked up by the halogen radical. Abstraction of proton lead to the formation of alkyl radical is a rate determining step you have mentioned. But how is it so? And why is it so? SN1 reaction, I said the first step, formation of carbocation, is the rate determining step. Why is it so? Because it all depends upon rates, which is actually happening the slowest step. The slowest step of the reaction is obviously the rate determining step. Since the slowest step is a rate determining step, in that step, whatever the species are there, more stabilization of that species we have to take. Okay?
Okay, sir. Yes, sir.
Okay, fine. It all depends. It all comes to rates only. And what rate depends upon? Rate depends upon collisions. Yes or no? The rate of a reaction depends upon the number of collisions, collision frequency. We know, we study the same from chemical kinetics.
Yes, sir.
Yes. CH3 C double bond of CH3 plus CH3 C double bond of H treated with OH minus upon heating forms what? Like 4 sets of products obtained. So self-aldol, and 2 crossed aldols. Ultimately, you get 4 sets of products, and these are the 4. Like if I take CH3 self-aldol, we have discussed for acetaldehyde as well as from acetone. Let us look at the crossed aldol CH3 C double bond of CH3 plus CH C double bond of H. Whenever this oxygen and these 2 hydrogens are lost, you get CH3 C double bond CH3 CH C double bond of H. This is one of the product which is a crossed aldol. And you can also have CH3 C double bond of CH plus CH3 C double bond of CH3. Oxygen and 2 hydrogens are lost, leading to the formation of CH3 CH double bond CH C double bond of CH3, which is again crossed. The remaining 2 are self-aldol. Self-aldol of acetaldehyde and acetone, and a crossed aldol between these 2 products will lead to the mixture of 4 products. C6H by C double bond of H plus CH3 C double bond of H. OH minus upon heating produce what? C6H by C double bond of H plus CH3 C double bond of H. Here you will get the first product. Here this particular aldehyde, benzaldehyde, does it possess the alpha hydrogens?
No.
No, sir.
Does benzaldehyde possess alpha hydrogens? It is not possessing the alpha hydrogens, yes or no? So it can't form the respective. It will not form the respective enolates. So you get CH2 minus C double bond of H is going to be formed, and the CH2 minus is going to attack this particular carbon. C double bond electron density moves away. You generate what? COH CH CH2 C double bond H is obtained, which upon heating will form C6H5 CH double bond CH C double bond of H, which is nothing but a major product. Yes or no? What is that product also called as? PH CH double bond CH C double bond H. Cinnamaldehyde. C6H5 CH double bond CH C double bond OH is also called as cinnamaldehyde. And what is crotonaldehyde? Crotonaldehyde is a product obtained whenever aldehydes undergo aldol condensation. Whenever you just take aldehyde, and if it is undergoing aldol condensation, then under that condition, whatever the product obtained, that is said to be aldol. C6H5 C double bond H, C double bond H, CH3. It will ultimately lead to the formation of PH CH double bond CH CHO, which is nothing but cinnamaldehyde. Everyone understood this point or not?
Yes, sir.
Yes, Nandana. Then I'll ask a question. Why can't the CH2 minus C double bond H undergo self condensation? Is there a possibility or not?
So there is a possibility.
But this is the major product. Why? Because the CH2 minus C double bond H, that is only formed. That is for sure, because the benzaldehyde do not have any alpha hydrogen. But the CH2 minus C double bond H, why it is attacking the benzaldehyde carbon instead of CH3 C double bond H? Because out of these two attacks, which is slow step?
It's attack of nucleophile slow step.
Yeah, attack of like CH2 minus attacking the benzaldehyde C double bond is slow. Yes or no? CH2 minus
Yes.
attacking the C double bond of benzaldehyde is slow because of T repulsions. So that is going to be the preferential attack, not the CH3 C double bond H. That will be the first step. So slowest step is the RDS. Look at this compound C double bond of CH, C double bond of CH3. Here you can have alpha hydrogen. Here this we have alpha hydrogen. So only one possibility. You can write C double bond OH plus CH3 C double bond O C6H5. So oxygen 2 hydrogens are going to be lost. You will generate C6H5, CH double bond CH, C double bond O C6H5. pH CH double bond CH, C double bond O C6H5. That is going to be the respective major product. Next comes the question intramolecular aldol condensation. I have told you this intramolecular aldol is combined with one more reaction. Very famous. Intramolecular aldol is always fused with which type of reactions? Like first you will do the ozonolysis. Yeah, very good. Ozonolysis and intramolecular aldol, they are always mostly asked in the, because if you do ozonolysis, no, of a cyclic ring, you get a two C double bond systems. The two C double bond systems can undergo intramolecular aldol to form again a different cyclic compounds. Intramolecular aldol will only happen whenever the cyclic rings are either 5-membered or 6-membered rings. Intramolecular aldol condensation is favored only if a 5-membered or 6-membered ring is formed. If you go with the CH3 C double bond or CH2 CH2 C double bond or CH3, where can you have negative charge? What are alpha position? This is alpha carbon. With respect to the C double bond, this is alpha, this is also alpha, this is also alpha, this is also alpha. Now let us try to pick up the alpha hydrogen. Where I can have negative charge? I can get the alpha 1, alpha 2, alpha 3, alpha 4. Negative charge I can have at alpha 1, alpha 2, alpha 3 or alpha 4. If I have negative charge at alpha 2, it has to attack this C double bond O. It will form what ring? At alpha 2, negative charge is obtained. That carbon of alpha 2 is attacking the C double bond O. How many member ring is formed? This alpha 2 and this C double bond O carbon are linked. How many ring is formed?
Three.
3-member ring. 3-member rings are possible or not possible? Intramolecular aldol reaction is going to happen only in such a way such that only 5-membered or 6-member rings are going to be possible. So here if I pick up the hydrogen from alpha 2, I will be getting a 3-member ring, so I can eliminate that. If I pick up the proton from the alpha 3, this alpha 3 has to attack this particular carbon. Again, how many member ring I am getting?
3-member.
3-member ring, so that is also not possible. So alpha 2 and alpha 3 I can eliminate or not? The carbon ion is never going to be found at alpha 2 or alpha 3 because they will lead to the formation of 3-member rings. But alpha 1 and alpha 4, again they are symmetrical. So if I try to pick up this or treat this with NaOH, it will form CH2 minus C double bond O, CH2, CH2, C double bond O, CH3. Because it is symmetrical, either I can pick up from this terminal or that other terminal. So this negatively charged carbon will attack the other C double bond O. So 1, 2, 3, 4, 5, 5-member ring I am getting, that is possible. 1, 2, 3, 4, 5. So I'll write the simply 5-member ring. On the 5th position, I have C double bond is converting into CO minus. 5th position also have methyl substituents. 4th, 3rd, 2nd, 1st. First I have CH2 only. On the 2nd, we have C double bond O. This will take water from the reaction mixture. It will form respective COH, CH3 and C double bond O. When you heat it, it will form. It will undergo elimination such that the C double bond C and C double bond O, they are in conjugation. So this is the major product. Okay, this will be the respective major product. C double bond O is in conjugation with C double bond C, and to the other carbon you have methyl group. Okay, this is nothing but your intramolecular aldol. So in the intramolecular aldol, there is different possibilities of choosing alpha hydrogen. First, you have to eliminate all those possibilities where you are getting the respective like 4-membered or 3-membered rings or 7-membered rings. First, you have to go with only 5-membered or 6-membered rings. Then in that, the nucleophilic addition, if you have to say, in case of unsymmetrical substances. So we have CH3, C double bond O, CH2, 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 C double bond O, CH3. This is alpha 1, this is alpha 2, alpha 3, alpha 4. Which I can eliminate? Which alpha carbons I can eliminate?
Alpha 2 and alpha 3.
Alpha 2 and alpha 3 I can eliminate, because if negative charge is possible here, they will form 4-membered rings. Alpha 1 and alpha 4, they are symmetrical or unsymmetrical?
Symmetrical.
Symmetrical, so I can pick any proton from any carbon. CH2 minus C double bond O, CH2, 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 C double bond O, CH3. Negative charge attacking this particular carbon. So that will lead to the formation of a 6-membered ring. Give numbering 1, 2, 3, 4, 5, 6. Yes or no? On the second position, you have C double bond O. Second is connected to first. First is connected to sixth. Sixth, you have CO minus CCH3. 6 to 5, 5 to 4, 4 to 3. This will pick up proton from water. C double bond O, CH3, COH. Upon heating, it will undergo elimination. It will form C double bond O, CH3 double bond. This is the major. Okay, C double bond O, C double bond C, CH3. That will be your respective major product. Look at here, alpha 1, alpha 2, alpha 3, alpha 4. Which I can eliminate? Which I can eliminate, students?
First and fourth.
First and fourth I have to eliminate, because this the first carbon gets negative charge that will attack this particular C double bond of, leading to the formation of 7-membered ring. 7-membered ring is not possible. So I can eliminate first and fourth. So I can form a double bond, negative charge, either on this position or on this position. They will lead to the formation of 5-membered rings. So CH3, C double bond O, CH minus, CH2, 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 C double bond O, CH3. This negatively charged carbon is now going to attack this particular carbon. What happens in that case? You get a 5-membered ring. This is 1, 2, 3, 4, 5. On the first position, you have C double bond O, CH3. Second, third, fourth, fifth, right? On the fifth position, you have what? CO minus CCH3. This picks up proton from the water, leading to the formation of CH3OH, C double bond O, CH3. This upon heating will form C double bond C, C double bond O, CH3 and methyl. So this will be the respective major. This will be the respective major product. Okay. So this is all about aldol reaction and cross aldol reactions and intramolecular aldol reaction. So next, Cannizzaro reaction. Cannizzaro reaction means aldehydes which do not have alpha hydrogen atom undergo disproportionation reaction. That means self oxidation and self reduction is going to happen, leading to the formation of alcohol and carboxylic acid. I'll discuss the mechanism here itself. Listen carefully. The aldehydes which do not have alpha hydrogen, I'll discuss the mechanism including the effect of isotopes also. HC double bond H formaldehyde I have taken and treating with the OD minus. OD minus. So what is going to happen? First, let us go with the simple reaction. Okay, don't complicate it. So OH minus only as of now you consider. First step is OH minus is now going to act as a nucleophile, attack the electrophilic carbon. C double bond electron density moves away, generating H, C, OH, CH, CO minus. this HCO minus COHCH, that will now undergo loss of hydride ion. In the first stage, the nucleophile is acting, the OH minus is acting as a nucleophile. In the second step, what happens? The negative charge on oxygen comes into, the hydride ion is lost. Loss of H minus, this is nothing but your RDS. HC double bond O COH. RDS is the removal of hydride ion. So the hydride ion which is lost, that will act as a nucleophile for the next molecule. HC double bond OH will be now attacked by the hydride ion acting as a nucleophile, and C double bond O pi electron density moves away, generating HCO minus CH and CH, which is nothing but CH3O minus. This CH3O minus will react with the HC double bond OH plus a CH3O minus. CH3O minus being basic in nature, it will pick up the proton, forming HC double bond O minus Na plus. If I take NaOH, you'll have Na plus and CH3OH. That means the same formaldehyde undergone oxidation to form the respective formate as well as reduction to form the respective methanol, alcohol. Same aldehyde undergone oxidation to form the carboxylate, undergo reduction to form the respective alcohol. Self-oxidation and self-reduction of the aldehydes which do not have alpha hydrogens, they those are called to be, that is called to be respective Cannizzaro reaction. That reaction is said to be the respective Cannizzaro reaction. Is that clear, students?
Yes, sir.
Yes, right. And aldehydes which do not have alpha hydrogens undergo disproportionation reaction, self-oxidation reduction to form respective alcohol and carboxylic acid. Mechanism, as I have told you, HC double bond H attacked by OH minus. OH minus acts as a nucleophile, forming HCHCOH O minus. HCO minus CHOH react with the next molecule. Here hydride ion is obtained, right? That hydride ion will act as a nucleophile. So it will form HC double bond OH, negative charge coming into the hydride ion acting as a nucleophile, attack the carbon. This is nothing but your RDS. RDS is the transfer of hydride ion B, since it is nucleophilic in nature, to the respective electrophilic carbon, forming formic acid HC double bond OH and CH3O minus. It is nothing but CH3O minus will pick up the proton from the formic acid, forming formate HC double bond O minus and a CH3OH. This is an example of disproportionation reaction. Aldehyde which is more reactive towards OH minus will be oxidized. Understand this point carefully. Second point, it is an example of disproportionation that you can understand because self-oxidation and self-reduction happen. Aldehyde which is more reactive towards nucleophile, that means whatever the aldehyde, if you have two different aldehydes, let us say, both are not having alpha hydrogens, the aldehyde which is more reactive towards OH minus, that will be oxidized because OH minus attacking whichever the species, that will form respective carboxylates. Yes or no? Aldehydes which is more reactive towards nucleophile OH minus will be oxidized. Ketone do not give Cannizzaro due to poor leaving tendency. If you have ketones, there the leaving tendency is poor. That is why they are not generally undergoing the respective Cannizzaro. And which aldehyde is more reactive? Aldehyde which is more reactive is oxidized, they are said. Among all the aldehydes, formaldehyde is always most reactive. Whenever formaldehyde is there, whenever formaldehyde is present in crossed Cannizzaro, reaction, it will always be Cannizzaro's reaction. It will always be oxidized as it is most reactive, towards OH minus. Is that point clear to everyone or not? Okay. So this was the mechanism of Cannizzaro and the details and different examples we are going to look at in the next class. Thank you all, everyone. Bye.
Thank you, sir.
Thank you.
Thank you, sir.